Okay, I just want to give you a way of visualizing some limited set of systems of differential equations in a very simple case. But I think this simple case is going to help us to understand and visualize solutions to these systems, and it will be helpful. So, yeah, let's look at a very simple fixed example of a system of differential equations. Let's look at this one. I'm borrowing this from the textbook. X prime equals 2y minus x. And the second equation will be y prime equals just x. Okay, now, first thing, just identify. The dependent variables here are called x and y. The independent variable, which you can't see here, I'm going to take to be t, time, okay? Because you don't see t in this system, we do call this an autonomous first order system of differential equations, okay? Because again, the independent variable is not visible, is not here in this system of equations. So we call it autonomous for that reason. This terminology should be familiar from what we did earlier in the course. Now, what I want to give you is a way of visualizing this system of differential equations. And I'm going to pull this visualization because it's hard to draw without a pre-made thing from the textbook. Here it is. Yeah, so please let me copy this. Copy image, and I'll drop it into this thing. Allow paste, and there we go. Here is the visualization of this differential equation. Now, how on earth was this generated? Let's take a closer look at it. This is what's called a vector field because it associates to each point in the plane a vector. Remember, a vector is a quantity. It's like a little arrow that has a direction and a magnitude. For example, you could imagine this is measuring something about the flow of air. I'm talking about like the wind. You might have seen like wind maps or something like that if you're interested in things like windsurfing or in sailing. If you look at maps of the ocean, there will sometimes be arrows to indicate both the direction of the wind, but also the strength, the magnitude of that wind. That's an example of a vector field. It's a vector field over the water. Here is anytime you have a set of vectors where you associate to each point in some kind of space a vector, that's called a vector field on that space. How was this vector field generated? Because I'm saying that this vector field is associated with this system of differential equations. So this vector field places a vector at each point x comma y in the plane. By computing x prime and y prime and using these as the x and y components. These as x and y components. So let me just take two examples maybe. So for example, let's take the point, how about the point 0, 3? Sure. X equals 0, y equal to 3. So at this point, if we plug in x equal to 0 and y equal to 3 into this system here, then what we see is that x prime is what we get by plugging in y equal to 3 and x equal to 0. And just doing the computation, we see that x prime is equal to 6. And y prime is equal to, well, if we plug in x equal to 0, we get 0. Make sure you understand how that happened. And so what that means is that at the point 0, 3 in this plane, I should see the vector with a x component of 6 and y component of 0. Let's see, it's 0, comma 3. And okay, it's hard to draw these things to scale, but the idea is that after you scale these things down, indeed, this is pointing in the 6, 0 direction at the very least, yeah? But it does have magnitude 6, okay? I mean, I guess you could try to draw an arrow that looks like that, but that wouldn't work if we tried to do this for every single point in the plane. So they shrunk it down. Let's just check one more point maybe. Let's look at the point maybe 2, comma 1. What would the x component be? Well, we compute x prime, and we plug in x equal to 2 and y equal to 1, and what we get is 0. I think I'm doing that right. And if we plug in x equal to 2 and y equal to 1 into y prime, we get y prime is equal to 2. So I should see a vector whose x component is 0 and whose y component is 2. If its x component is 0, that means it should be vertical at 2, 1. I don't know. Is that true? 2 is here. There's 2. 1 is here. And yeah, I mean, it's hard to say exactly because there isn't a point right there. But you can see that the vectors around it appear to be pointing straight up and vertically. So yeah, this is the visualization. Now, let me just say, what does it mean to solve one of these differential equations? It means to find a path which follows these arrows, where these where the arrows are the velocity vectors for this path. So finding a solution means finding an x of t and a y of t which satisfies this system of differential equations. And that's a parameterized curve through the plane. Let me show you an example of such a curve. And maybe I'll suppress the stuff about existence and uniqueness and just let you read about that. Here's that example. I'll just let you look at it here in the textbook. You can see that at every point, the vector field is tangent to this solution curve here. So you can figure out the trajectories of things that are under the influence of this particular vector field by solving this differential equation. Okay? I'm going to leave off the stuff about existence uniqueness and just ask you to go read the textbook. You'll see it here. It's in this section on Picard's theorem. All of the systems that we're not going to focus on the pathological situations too much. All of the situations that you're going to find yourself in, all the systems that you're going to be working with will obey the assumptions of Picard's theorem, which guarantees the existence and uniqueness of solutions to first order systems with initial conditions. Okay, so-called initial value problems. All right? But we'll take that for granted, and you can ask me about it like in office hours if you're deeply curious. Okay, that's enough. See you in the next one. Bye.